Morning, everybody. We're going to start on our final section of learning for this semester, which is going to be sequences. So this is going to be out of chapter 5 in your red books. And what we're going to look at today is mainly just regular number sequences, and then we're going to pivot to arithmetic sequences. So in mathematics, one of the things that we practice and that we can apply to real life is to run through this process for a sequence. And the process involved with the sequence is that, first off, you have to recognize a pattern in a set of numbers. We need to be able to describe whatever pattern is occurring. And typically we do this in words. You could also do this in graphs. And then ultimately we need to be able to continue the pattern, apply that pattern, use it to make predictions. Because if you recognize that pattern, you can keep applying it to make predictions on what should happen. And so when we talk about this word sequence, we're going to define a number sequence as an ordered list of numbers defined by a rule. This rule can be addition, it can be multiplication, it can be some other type of rule, but it has to consistently occur. And so when we talk about the numbers in this sequence, we're going to refer to those as terms. And you should have seen a little bit of this before in Algebra 2. So some of this may come quickly. Some of this we may need to review a little bit more. So then when we're talking about the explicit formula, when we use that word, that's the equation that's going to give you the nth term or a general term of a sequence. And we'll get more into the explicit formula here in a little bit, but just some vocabulary so that we know what we're talking about with this stuff. So then the general term or the nth term of a sequence is going to just be represented with a symbol with a subscript of n. So like we could use un, u sub n, t sub n, lowercase t sub n, big A sub n. And all that means, like if you see u sub n, this represents the sequence that can be generated by using un as the nth term. Now, it can be a little bit confusing looking at some of this terminology. So if you're confused about anything, please let me know and we can get it sorted out. So unless it's stated otherwise, we assume that the first term of the sequence, we denote that with like u sub 1. So whatever the number is, that represents the term in that sequence. And that sequence is defined anytime that n is a part of the positive integer. So it has to be like 1, 2, 3, 4, 5, and so on. Sometimes you might choose a sequence to start with u sub 0. Especially if we're talking about investments or we're talking about time, it is good to start from 0 that way. And the last thing, kind of what we're going to be doing here in a little bit, is we're going to be using technology to help generate sequences from a formula. So we're going to be using a calculator to do so. So if you need a app, I recommend Wabitamu if you got an Android, or I recommend Graph and Calc 83 if you've got an iPhone, and we will go from there. So the first thing we're going to do with sequences is we're just going to try to make some pretty basic predictions here. So the first sequence that we've got here, sorry about that, you all. We want to describe the sequence 14, 17, 20, 23, and we want to write down the next two terms here. So if we've got those, we want to try to describe what's going on. We want to use words to do that. So to me, so look at that real quick, see if you can, so if you're going to put that in words, how would you do that? So for me, I'm going to say, oh, come on, I need to get a pen that actually works, I suppose. So for me, I would say that we're going to add 3 starting with 14. That would be good for putting it into words, because when you're putting it into words, you should be able to describe it well enough so that if you go get your mom or dad or your little brother or little sister, that they can go and they could write out the sequence from what you've told them. So then we're going to say, okay, add 3 starting with 14. So then the next two terms would be 23 plus 3, which is 26, and then 29. This is an arithmetic sequence here. This is an arithmetic sequence here. So then the next one that we're going to look at here is we're going to identify the pattern here and state the next two terms. So we go 3, we go 9, we go 15, we go 21. So take a second and think about it. So in words here, we're going to say add 6 starting with 3. We're starting with 3 here. And so I'm just going to go ahead and write that word. This is anytime that you're adding or subtracting the same thing each time, we do refer to that as arithmetic. We're going to get to that here in a second. But it's got to be the same thing every single time. So here we're adding 6, and then our next two terms here would be 21 plus 6 is 27. 27 plus 6 is 33. Now, the last sequence here, I want you all to take a second and pause the video and see if you can figure out right here what the pattern is with this sequence right here. Because it does involve adding, but it's not an arithmetic sequence. It does involve adding, but it is not arithmetic. So pause it, see if you can figure it out. If not, that's okay. But it is a famous sequence. It's what's known as the Fibonacci sequence. And the Fibonacci sequence is a famous sequence. It's found everywhere in the world, in nature and whatnot. And basically, to sum up the Fibonacci sequence in words, is that you add the previous two terms together to get the next term. And so if you're looking at this now, like if this 2 came from doing 1 plus 1, this 3 came, we did 1 plus 2 and got the 3. 5, 2 plus 3 gave me 5. To get 8, we did 3 plus 5 gave me 8. So then to get the next term in front of this, we're going to say, okay, well, 5 plus 8. So the next term in that Fibonacci sequence is going to be 13. And then I'm going to add 8 and 13 to get the next one, which is going to be 21. And we can get into more of the uses of the Fibonacci sequence at some point, but it's important to note that this is not arithmetic. We are not adding the same thing each and every time. We are adding something different each and every time. And so with that, we're going to use this to springboard into arithmetic sequences and kind of the algebra that goes with these things. So when we're defining an arithmetic sequence here, we're going to be defining this as a sequence in which there's either addition or subtraction of a common number. So we need to be adding or subtracting the same thing each and every time. And we refer to this common number that we're adding or subtracting as the common difference here. That's the amount it increases or decreases by each term. And so the thing is here, if we know a sequence is arithmetic, we can use a formula to find the value of any term of the sequence. And that's what we referred earlier as the explicit formula. And so if we want to do some general terminology here, so suppose the first term of an arithmetic sequence is u sub 1 and the common difference is d. So we would get the second term, u sub 2, by doing the first term plus the common difference. We would get the third term by doing u sub 1 plus 2 times the common difference, or 2d, because that would be d plus d. And we'd get the fourth term by doing the first term plus 3 times the difference, So the first term plus D plus D plus D, and so on and so forth. And because of that, our explicit formula here for UN, for any nth term, for any term that we're trying to find there, we're going to define that as the first term plus n minus 1 times the common difference here, times this common difference. And so with that, we can use this formula. If we can identify that a sequence is arithmetic, we can use this to figure out a bunch of different things. And so with that, I'm going to move this page here, and we can kind of get to looking at this now. So the first thing that we're going to do, so this is, if you're wanting to follow along in the book, we're going to go to example 2 on page 105 in that red book. So we've got this string of numbers. We got 2, 9, 16, 23, 30, and what we're going to answer a couple of questions with this. So I'm going to go ahead and write that explicit formula here. Explicit. So the first thing we want to do is we want to show this sequence is arithmetic. So as a reminder, it's arithmetic, but it's got a common difference. So I'm going to just look here. Okay, I add 7 there, add 7, add 7, add 7. So that is good enough to show something is arithmetic. We add or we subtract the same thing the entire time. The difference there should be the same thing. So now the next thing we want to do, we want to find a formula for the general term here. For the general term here, we want to find a formula. So with that, we're going to lay this out. We're going to do the explicit term. We're going to say the general term U sub n is equal to the first term there, the UN, which is, or U sub 1, excuse me, 2 plus, we're going to say n minus 1 times the common difference here, which is 7. And to make your all's lives easier, I would simplify this. So what I mean when I say simplify is we're just going to distribute there. So we're going to call this U sub n equals 2 plus, let's see, n times 7 is 7n minus 7. And I'm going to simplify this again. I'm going to combine these like terms to U sub n equals 7n minus 5. And that right there is our formula for the general term. This is our explicit formula right here. And what that's going to do, the reason we simplify that is now all we got to do if we want to find what value a certain term is, all we have to do is just substitute n for n. We don't have to worry about punching it into a calculator or anything of that sort of nature. So if we want to find the 100th term of this sequence, if we want to find U sub 100, the 100th term in this sequence, what we're going to do is we're going to replace, since we replaced that n right there with 100, we're going to do the same thing there. We're going to say 7 times 100 minus 5. And so as a result, our 100th term in the sequence, if that pattern holds, we're assuming it does, is going to be 695, 700 minus 5. And what we can also do is we can set up, we can figure out will certain terms be parts of this sequence. And the way that we will do that is that, like, for example, if we want to answer the question, is 828 a term of this sequence? We're going to set 828 to the general term here, to the U sub n. We're going to say 828 equals 7n minus 5. And we're just going to solve this right here. And if we get a whole number term, it's going to be a term. If it's not a whole number, it will not. So let's see real quick. I'm going to solve this. So I'm going to add 5 over to get 833 equals 7n. I'm going to divide both sides there by 7 to get that n equals 119. And so since this, when I work this out, when we do this math here, we get n is 119. That means 828 is the 119th term. So we can say with certainty, hey, yes, this is in fact a term of this sequence up here. Really quick way to confirm it. If you want, you can be my guest. You can write out 119 terms and you can confirm that for me. So then the other one here, we're going to do, we'll say 2,341 equals 7n minus 5. So same process here. We're going to add 5. 2346 equals 7n. We divide both sides here by 7. And let's see here. I need to get a calculator for that. I don't know that one off the top of my head. 2346 divided by 7 is 335. So we're going to say n equals 335.1. And because this is not a whole number, it is not a term in the sequence. Like when we're counting terms of a sequence, we can only count whole number ones. Because this is not a whole number, we're going to say no, that doesn't work. Because that is not a number. And so some other things that we can do with arithmetic sequences here and arithmetic patterns. So we're going to do a little algebra exercise here, kind of to tie in the mindset that we need to have here. So what we need to do is we want to find k. We're given these three terms here. The three terms that we're given are, we've got 3k plus 1. That's one of these terms. We've got k here, and we've got -3. These are our terms in this sequence here. And we want to know what the value of k is that would make this an arithmetic sequence. And so as a reminder of an arithmetic sequence, it's arithmetic if we can add, or if we can add the same thing to each time. Or you can think about it, if I do this minus this, I should get the same thing if I do this minus this. So I'm going to set this up. So the difference here should be k minus 3k plus 1. This is the difference right here. And since it's a common difference, it should be the same as the distance between these two numbers. So I'm going to say -3 minus k. Now these two things, these two distances here that we've just written, should be the exact same if this is truly arithmetic. So we've just got to solve an equation here. So we're going to say, okay, well, this is going to be k minus 3k minus 1 equals -3 minus k. And now we've got to solve it. So let's see here. So k minus 3k is -2k minus 1 equals -3 minus k. I'm going to bring this 2k over. So let's see, plus 2k and plus 2k. We get k, -3. That's going to be a plus k equals -1. So we're going to get the value, when we add that 3 over, we're going to get the value of k equals 2. And just to make sure that that works, let's substitute 2 in here. So 3 times 2 gives me 6 plus 1, so that term would be 7. This term right here, k is just 2, would be 2, and then -3. And you can look and see that when we substitute that in, that we get the exact same numbers here. Or we get an arithmetic sequence here. It's going down by 5 each time. So that's just a quick little algebra exercise with arithmetic sequences. So the next example that we're going to look at is how do you write an equation, how do you write an explicit formula for when you're given terms that aren't the first term. And so to do this, so we're given the third term. So let's see here, 1 and 2 and 4, 5, 6, 7, 8. So we're given the third term. So like this is the first term, this is our eighth term. So we've got 8, and the other term that we've got here is negative 17. And we want to know, okay, we want to try to write an equation of the form un equals u1, the first term, plus n minus 1 times the common difference there. And so to do that, what we've got to figure out is that if this is the third and this is the eighth term, we've got to figure out how many times, how much do we decrease in that many terms. So to do that, what we can do is almost take the slope of those points or figure out the distance of these. So 8 to negative 17, we got to figure out the distance between those. So to do that, we're going to say 8 minus negative 17. So we're going to say 8 minus negative 17. We're trying to figure out how far apart are these numbers. And honestly, you could do this either way. I realized I just did it. I could have done it an easier way, but it will be okay. So then we're going to say, okay, well, that's going to be 8 minus negative 17. 8 plus 17 is 25. So then we do that 25 over a certain amount of terms. So that's going from the third minus the eighth, which is going to be negative 5. So we hit that term going a distance of those terms of negative 5. So let's see. So that's going to be, the distance is negative 5. So the common difference here that we're going to be subtracting each time is going to be negative 5. And so from there, what we can do, let's see here. So we've got the difference. So we've got u sub n equals u1 plus n minus 1 times negative 5. But what we need, we still don't know exactly what our first term is. We still don't have a great idea of what our first term is. And so to do that, what we're going to have to do is say, okay, well, we can substitute in some information. We could also go in reverse. Either way works. Just to get us more comfortable with the formula, I'm going to work within this general formula here using this information right here. So we know U3 is 8. So if I set this U3, if I say 8 equals U1 plus 3 minus 1 times negative 5. This should help me figure out what U1 is. So we get 8 equals U1 plus 2 times negative 5. That's going to be minus 10. So U1 minus 10 is going to be 8. You all can probably figure out that that is going to be 18. Some of you all are probably looking at that and saying, Mr. Price, why didn't you just say, well, we're subtracting 5, add 5, that's going to be 18. That is a fine way of doing it. But if the number is larger than the third term, let's say I gave you the 30th term and the 70th term, it gets a little bit more troublesome to calculate. I know you all are practical. I appreciate that about you all, but also we need to make sure that we understand how to work within the with saving ourselves some time using that formula. So with that, I'm just going to simplify this to make it easier to work with in the general form. So I'm going to say, okay, so distribute there. So u sub n equals 18 minus 5n plus 5. So then the general form here is going to be 23 minus 5n, or you could see that either way. You're typically going to see it with the n written first. But both of those are equivalents. So we're going to be subtracting 5 multiples of 5 from 23. So we're almost finished up for the day. But we do need to continue. We're going to wrap up with 2 problems here. So the first one that we're going to look at here is we're going to look at the example 5 on page 108. And what we're going to try to do is we're going to insert 4 numbers between 3 and 12 so that all 6 numbers that we have are arithmetic. So the first number we've got here is 3. So we've got 1, 2, 3, 4, and then our last number here, which is 12. So we've got the first term, and we've got the 6th term. And what Mr. Price is going to do here is I'm going to actually do this one a little bit easier so we don't have to deal with all those negative signs on this one. So to do this, what we've got to figure out is how much our average leap is. So to do that, we've got to think to ourselves, okay, the distance between 12 and 3. So you all are probably thinking to yourself, Mr. Price, well, I can do that. That's just 12 minus 3. So we're making that jump of 9 there over a certain amount of terms here. So from the first term to the 6th term, let's see, that 6 minus 1, that's going to be a distance of 5. So the amount that we're jumping up each time is 9/5, or 1.8. So when we're looking at that, so when we're filling in these terms, all we've got to do is say, okay, well, we're just adding 1.8 each time. And so to do that, we just say, okay, well, 3 plus 1.8 is 4.8, then 6.6, then 8.4, and then 10.2. All we're really doing is we're filling in, once we know the difference, we can very easily fill in those numbers. And so for the last thing for today, we're going to look at example 6 on page 108, and we're going to be looking at old Ryan the cartoonist here. Old Ryan the cartoonist. So his comic strip has just been bought by a newspaper, and he sends them 28 comic strips he's drawn so far. And every week after that, he's a hard worker. He's like, I'm going to send 3 more comic strips each time. So the first thing we want to do is find the total number of comic strips sent after 1, 2, 3, and 4 weeks. So when we're listing those out, that's just going to be as easy as saying week 1, and then 2. I'm just going to do ditto marks here. 3 and 4, so week 1 was 28, and then 31, and then 34, and then 37. And so then the next thing that we're wanting to do here is we're wanting to show that the total number of comic strips sent after is an arithmetic sequence. So to do that, all that we've got to show is that there is a constant difference here. So from week 4 to week 3, 37 minus 34. Let's see, 34 minus 31 and 31 minus 28. All of these things should give us a constant difference. And if there is a constant difference, it is arithmetic. So then what we want to find out here is, okay, find the number of comic strips sent out after 15 weeks. So to do that, I'm going to stray away from adding 3 that many times. I think that we are in an advanced math class here. I think that we can stray away from doing that. I did write this as a U instead of an A. That's my fault. That is Algebra 2 sneaking in there. And when you all learned this explicit formula, you probably did learn it using A instead of U. That is just the notation that IB prefers to use here for whatever reason. I'll have to ask about that one. So we want to find the number of comic strips sent after 15 weeks. And so when we're doing that, we're wanting to find U sub 15. Now the first week here, the first term there was 28. And another way for you all to think about this, if we're going to do this, go from week 1 to week 15, you just need to think about how many times, if I'm going from week 1 to week 14, would I add that difference of 3? And it's always going to be 1 less. You can always help make sense of these formulas when you're using them. And if you can do that, it will help you out big time. It will help you out big time. You will not get as confused with things. You'll find it's a little bit easier to work through if you'll just take a second and ask yourself, why am I substituting in to this formula right now? And if you don't know, feel free to ask me. I do not mind to explain that at all. So after week 15, he will have sent 70 comic strips there. 70 comic strips. And so the last thing for today, and we're going to look at, is we want to know, okay, when is Ryan going to send his 120th comic strip here? So if we've got that explicit formula that we were using, let's see here, it was U sub n equals, now his A1 here was 28 plus n minus 1 times 3. And so we've got to ask ourselves, what are we trying to find if we want to know when does Ryan, so like which variable are we trying to find? And so this 120 here, we're going to set equal to U sub n. We're trying to find the number of week. What number week does Ryan send that? So we're going to say this is 120 equals 28. And I'm going to go ahead and distribute this right here, 3n minus 3. And we're going to go ahead and solve this right here. So let's see. That's going to be, I'm going to combine those like terms. 25 plus 3n equals 120. Subtracting 25 is going to give me 95 equals 3n. Solving is going to give us n equals 31.6 repeating. We're going to round that to 31.7 weeks. But here's the thing. When we're working in sequences here, we cannot have decimal values of n. We can't have decimal values of n when we're working with these arithmetic sequences. So we're going to round this up to 32 weeks. Up to 32 weeks. So if you all have any questions on what we've gone over today, please let me know. We can schedule a time to meet together on Zoom and figure that out, or you can shoot me an email. And I hope you all have a good rest of your day, and I will see you next time.